So now we're ready to look at the third alkylation reaction, and this one is called the acetoacetic ester synthesis. And it's almost exactly the same as the malonic ester synthesis, just uses a different starting material. But for the most part, you're going to see it's really exactly the same thing. So this is acetoacetic ester, looks almost the same. And this is going to be either a 3 or 5 step reaction depending on how many alkyl groups you want to add. You are still going to start the reaction with sodium ethoxide, or OET minus, and you're going to end the reaction with H3O plus and heat. And you are going to add an alkyl halide, 1 or 2, depending on how many, like I said, how many you want to put onto the molecule. The difference here is that your product, instead of being a carboxylic acid, your product will be a methyl ketone. And let's mark the carbons that are staying from the acetoacetic ester into the final product. So you can probably imagine if you wanted to do this in a 5-step process, we would do step 1, ethoxide, step 2, an alkyl halide of our choice, step 3, another round of ethoxide, step 4, another alkyl halide, and then step 5, hydrolysis, which is H3O plus, and heat. And we again are going to make a methyl ketone, this time with 2 alkyl groups, same 3 carbon atoms that are staying in the molecule through the whole process. Let's draw the mechanism for this reaction. You're going to see that it's really similar, it's really identical to the malonic ester. So because it's so similar, we're only going to do a 3-step this time instead of a 5-step like we did for the malonic ester. The first thing that happens, as you know, is going to be deprotonation of the alpha carbon. And you do have 2 alpha carbons in this molecule. You've got an alpha carbon over here that could possibly be deprotonated, but that alpha carbon in the middle, it's like extra alpha because it has carbonyl group to the left and carbonyl group to the right. So that one is definitely the most easily, those hydrogens are the most easily abstracted. So let's use ethyl bromide as our alkyl halide, and here is our SN2. It's adding that alkyl group to the alpha carbon, and then let's pretend like that's good enough. We don't want to add another alkyl group to this molecule. So now we will go ahead and do the hydrolysis H3O plus with heat. This is the reaction that you learned in chapter 21 when we were learning about the reactions of carboxylic acid derivatives. This is converting an ester to a carboxylic acid. And again, we want to redraw that carboxylic acid, twist it around to make it easier for us to visualize that rearrangement that's about to happen, that Diels-Alder looking reaction. And I always like to start with carbon-oxygen double bond. I'm not sure why, when I'm moving the electrons around in this reaction. So this is a rearrangement that occurs. This process right here, we call decarboxylation because we are removing CO2. And let's draw what we get. So I'm going to start with the carbonyl group on the left. And then I'm going to move clockwise. So the carbon-oxygen single bond has become a carbon-oxygen double bond. There's that CO2. The oxygen-hydrogen bond broke. We created a new oxygen-hydrogen bond. That oxygen-carbon double bond is now a single bond. Carbon-carbon single bond is now a double bond, and the other carbon-carbon bond broke. So our molecule looks, it just looks kind of weird, but there it is. So let's redraw to make this prettier. Our CO2 molecule, this guy, CO2, which looks funny as a line structure, and our enol. And I want to make sure that I have the right number of carbons. 1, 2, 3, 4, 5 in my chain. 1, 2, 3, 4, 5. And the enol undergoes tautomerization because the carbon-oxygen double bond is more stable than carbon-carbon double bond. Looks good. There is our product. So let's go back up here and highlight I'm going to use a different color, the carbon atoms that started in this reaction, that stuck with us through the reaction. Oh, see, yeah, I thought maybe I might have, no, that looks good, we're good. I have insecurities about having the wrong number of carbon atoms, which is why I'm going through and picking on them and making sure that I haven't done too much. Now that looks beautiful. And there's our molecule. So let's go check out the worksheet. So here is a methyl ketone, and we can synthesize methyl ketones using the acetoacetic synthesis. So this problem is asking us, how would we go about doing that? What would we need to add? So if we're doing acetoacetic, we're always starting with this guy right here. And we have the potential for 5 steps in this process. I'm just going to go ahead and do 1, 2, 3, 4, 5. And we always start with ethoxide. And we always end with H3O plus and heat. And if we need all of those steps, step 3 is going to be an ethoxide as well. So what we need to do is identify in our product which carbon atoms are coming from the acetoacetic ester, because that is going to help us choose the correct number of carbon atoms in our alkyl halide. So it's really important that you know that this carbon that I'm making red right now is not being added in the reaction. It's coming from the acetoacetic ester. So there's the R group that we need to add. And we don't need this step 3 or step 4 because we're only adding one R group. And so there it is. That's all there is to it.